Okay, this screencast is going to talk about kind of a review for the kids that were in class all week about magnetic flux, but for the guys who are on Kairos, this will be specifically it'll be your introduction, I guess, to magnetic flux. But let's start off by realizing that we know that a changing current produces a magnetic field. I should use B field, right? And we know the question was, would a changing B field produce a current? Okay, so this was moving charge, right? So we had moving charge created a B field. That was the very first lab we did in this unit where we had the vertical wire and we had charge going down there, and you guys had compasses and you saw the compass respond to a magnetic field created by the current. So my hero, of course, Michael Faraday, investigated if a changing B field could produce a current. And so he did an experiment where he had a primary circuit and a secondary circuit, and in the primary circuit he created a current, turned it on and off, and found and discovered something, and that's on our next slide. Don't pay attention to this right here, because this is from notes that I gave in previous years in a different textbook. So for you guys it would be chapter 18 for magnetic flux, changing B fields. This is chapter 17 for you guys. But basically, here was Faraday's experiment. Let me shrink this down a little bit. Scoot it up here. And then I got to get rid of this. Okay, I just had to get rid of my old writing. So Faraday's experiment was, again, based on Hans Christian Oersted's discovery that a changing or a current changing moving charge created a magnetic field. He actually created a experiment where he had a primary circuit here on the left with a solenoid, all those loops of wire there. He put an iron core through the solenoid, and then the secondary circuit over here also has a solenoid right here, and doesn't have any source of potential difference. It just has an ammeter. Actually, it's called a galvanometer. It's a very, very sensitive form of an ammeter that measures current. So the galvanometer was able to measure any current in the loop. So what he did over here is he closed the circuit, and there was a battery right here in this circuit, and a current went through that circuit. As a result of the current, you know that a current through the coils there creates a strong magnetic field. In this case, the current is going to the left coming out of the battery, so it's going to the right here coming into the coil. Since the coil wraps around the back side of the magnet first, then on the top of the magnet, or on the top of the iron core, I should say, top of the coil, it's rotating in the direction I'm showing there. So if you grab that with your with the right hand rule, you would see that it's creating a B field going this way. So that changing B field, as he closed and opened the circuit, he saw that it actually produced a reading on the galvanometer over here. So there was an induced current. And he only saw the reading when he closed and opened the switch. So when the current was changing, over here on the right in my notes in black, when the current was changing in the primary circuit, there was a current in the secondary circuit. The conclusion over here is that a magnetic field created by the changing current in the primary circuit, let me scoot up here, oops. Now I got to get rid of all my scrawls, or at least move them. How about that? A changing current in a magnetic field, changing magnetic field created by the changing current in the primary circuit creates a current in the secondary circuit. We call that an induced current, and it's induced because it's not created by a battery. It's a current created by what we are going to call an induced, I keep forgetting to change my tool there. is created by an induced EMF down here. So a current is a current whether it's created by a battery or whether it's created by a changing magnetic field. So it's no different than a current that would be created by a battery. But this is called an induced EMF because it was induced by a changing magnetic field. So as Faraday studied this, he realized that the magnitude of this induced EMF depends on a lot of things. It was proportional to, and when I say proportional to, I mean directly proportional to, the number of loops in the wire. So the more loops, since it's proportional, directly proportional, the greater the induced EMF or potential difference. It was also proportional to the strength of the B field. So the stronger the B field, the greater the induced EMF, the greater the current. It was directly proportional to the rate at which the B field changes. So if you changed it more rapidly, so a quick change in the B field produced a larger induced EMF. So when delta T is small, you had a large induced EMF. The area of the loops affected the intensity of the induced EMF. The larger the area of the loops, the larger the induced EMF, the larger the current. The angle between the B field and the loops mattered as well. So if you had a circular loop or a rectangular loop that was exactly perpendicular to the plane of the B field, and all the B field lines, if you think of it that way, went through the area of the loop, it was a very strong induced EMF. If you rotated the loop so that the plane of the loop was parallel to the B field lines, you didn't get any induced EMF. So the angle was important too. So he put all this into an equation. Actually, he first defined a concept called magnetic flux. Physicists defined this. I don't know if Faraday was the one that actually did this, but magnetic flux is a measure of the number of B field lines that pass through a given area. And it uses this Greek letter phi, or phi. I usually call it phi. So phi is magnetic flux. And you can think of magnetic flux as just the number of B field lines going through a specific area. Usually the area is a circular loop. It might end up being a rectangle or something like that. But move that out of the way. Here you see a loop that is basically perpendicular to the plane of the page right here. Sorry. Perpendicular to the plane of the page, and you see the B field lines going directly through the loop. So when the plane of the area is perpendicular to the B field, the greatest flux occurs. And the measurement of flux is the magnitude of the B field times the area of the loop times the cosine of the angle theta between a line that's normal, that means perpendicular, to the area of the loop and the direction of the B field. So notice that the normal line here is exactly parallel to the B field. That means the area of the loop is perpendicular because the normal line is perpendicular to the area. So the normal line and the B field have a angle of 0, cosine of 0 is 1. So that's when you'd have the maximum flux through there. Now don't think of flux as like a change. Flux, like we would use it in everyday English. You know, my life is in flux because there's some change happening in my life. Flux in this case is just the number of B field lines times the amount of area it goes through. So the flux certainly can change. There's a lot of things that can change that flux, but you don't have to have change to have that flux. As you can see here, flux is just a product. Magnetic flux is a product of B field strength, area, and the angle between the two. So you don't have to have any change to have that flux. Okay. So I've moved down the page a little bit here. Notice how if the angle of the if the angle of the loop changes a little bit, the angle of the normal changes, and now cosine of theta is not a 0 degree angle anymore, has a little, it's going to be smaller, 0.8, 0.7. So this number now becomes less than 1, and this angle, or this value of magnetic flux becomes smaller as the area rotates relative to the B field. The units of flux are Tesla, because that's our magnetic field units, times area, square meters. So you got Teslas times square meters. It's not Tesla per square meter. It's Tesla times square meter. That's known as a Weber. That was a guy, another scientist. So WB is another unit, kind of like a Newton times a meter being called a joule. A Weber is a Tesla times a square meter. Okay, next page. So here's the quantified value. Here's how you can actually quantify the induced EMF for a changing magnetic field, and how it induces a voltage in a secondary circuit or in a loop. It doesn't have to be a secondary circuit like Faraday's law. It could just be a changing flux that induces a current and an EMF in a loop. So E, is potential difference. It's in this case referred to as induced EMF. It's dependent upon the number of loops, and it's dependent upon a changing flux. So this is a changing flux with time. Time's in the denominator, and the flux is in the numerator. But flux is change of B times A times cosine theta. So there's a lot buried in that little flux symbol there, that delta phi. So it's directly proportional to any changes in the magnetic field, any changes in the area, any changes in the angle. Okay, so we've captured all of those things on that previous slide that we said the induced EMF was dependent upon magnetic field, area, angle, time, number of loops. All of that is in this simple equation, but we've defined this quantity flux to capture the magnetic field, area, and the angle, all in one term there. So the negative sign there talks about, your book doesn't use that, but most textbooks do use it. Your book just talks about the magnitude of the induced EMF, and then it talks about how to determine the direction of the induced EMF, which is another principle called Lenz's law. So before I get into that, let's talk about some examples of how things can induce an EMF. Your textbook actually has 3 different sections. I think it's 18.7, 18.8, 18.6, 18.7, and 18.8 that all talk about different ways that an induced EMF could occur by varying one of these terms. 18.6 talks about changing the magnitude of the B field. 18.7 talks about changing the area to induce the EMF, and 18.8 talks about changing the orientation of the wire so that the angle changes, so that you get a changing flux that way. So in this little example problem, though, this is a numerical problem, but before I get into the numbers, I want to just kind of talk through it for a second to kind of give you an idea of how things can change to produce the magnetic field, or whatever can change to produce an induced EMF. Here's a magnet with the North Pole facing to the right. The magnetic field lines come out of the North Pole to the right. As you move this magnet closer to the loop, you see the 2 lines here on the outside that previously didn't go through the loop. Now all will go through the loop. So you're increasing the magnetic field lines, therefore increasing the flux through that area of loop. So the increase is in the B field going this way. And that's going to be important when we talk about, I should put a delta there. That's going to be important when we talk about what direction the current will go as a result of that change. But I'm going to hold off on that just for a second as we just talk about what are some of the changes that could occur. As seen, I could rotate this loop, kind of right or left, and that's going to change the area of the loop, which is going to reduce the number of lines that go through the loop. That would also change the flux. I could do it quickly, move this quickly or slowly. The changing flux as the time factor changes. If I move this magnet more slowly, you'll have a smaller induced EMF and a smaller current. So as delta T gets larger, I move slower, you get a smaller induced EMF. If delta T is quicker, then your induced EMF tends to be larger because it's in the denominator on the right side. What else could I change? I could change the area of the loop. That would be like scrunching the loop down, keeping it in the same orientation, so I'm not rotating it, but scrunching the loop down or widening the loop, believe it or not, would also change the amount of flux, because that would increase or decrease the number of magnetic field lines going through the loop due to the smaller or larger area. The number of loops, I could keep everything else exactly the same magnet, same amount of motion, or same velocity, I should say. So the same delta T in the denominator. I could keep the orientation of the loops the same, but just increase the number of loops. So I could add a few more loops here, and by changing that N, I would increase the induced EMF. So those are the factors involved. I'm going to go ahead and leave it to you to try and solve this problem based on the given information. And it talks about calculating the induced EMF, which obviously you're going to use Faraday's law to do that. And then part B asks, based on that induced EMF, try to calculate the induced current. Well, if you know the resistance, which they give you here, 3.55 ohms of the coil, and you know the induced EMF, that's just like a potential difference, you can use Ohm's law to calculate the induced current. So I'll let you do that on your own, and I will talk now about how you determine the direction of the current that results from this induced EMF from the changing magnetic field. Okay, Lenz's law, he was another scientist that in the 1800s was able to determine a rule for how which direction the current would flow based on the changing flux. And the law reads like this: an individual current always flows in a direction that opposes the change that caused it. So it opposes the change that caused the current in the first place. So if you think about there's a certain amount of flux going through this loop right here before this magnet starts to move. So there's a certain number of magnetic field lines that are going through that area of loop, and then I decide to move it. If you think about it this way, that loop doesn't want the amount of flux to change through it. It will create a current that opposes that change. So in other words, I've got a certain number of field lines going to the right, probably use a different color here, a certain number of lines that are going to the right. As I move this magnet to the right, I increase the number of lines that are going through to the right. So as a result, the current that is produced by that will make a magnetic field that goes to the left to fight the increase of the lines going to the right. So in order to produce a current so that the magnetic field points in the opposite direction of that was just increased, the current in the loop has to go, on our side of the page, it has to go this way. And if you use your magnetic field right-hand rule where you curl your fingers around the top of the wire, then you can see that your fingers will curl towards the left and your thumb will point into the page at the top of the wire here, so that it creates a B field going to the left from the induced current. That will fight the increased flux going to the right that's caused by the magnet moving to the right. So that's kind of a lot to think about. It takes a few, problems, and we have a setup in the physics lab at school where you can practice the Lenz's law to try and predict when you change a magnetic field a certain way, how the current will react. And I would encourage all the kids that have been on Kairos to do that. On the right side figure here, let's just do this one more time. Now, instead of moving the north pole of the magnet towards the loop, I'm going to move the magnet to the left, so the north pole is moving away. North and south pole are moving away. but you're decreasing the flux that is going this way. Since you're decreasing the flux going to the right, the current that's produced is going to want to replace that was lost. Okay, it wants to stay the same. Again, think of it that way. So it's going to produce a field that wants to go to the right. Okay, so if it wants to produce a field that goes to the right, it has to create a current. Again, your right-hand rule for your magnetic field is going to be down from the top of the wire, and so it's going to produce, if you curl your fingers, it's going to produce that B field going that way to try and replace the magnetic flux that it's losing. Hopefully that makes some sense to you. I know this is kind of a tough topic, but you know, again, I encourage you to come into school early one day this week before the test on Thursday to try and practice this in the back of the room, and I think it'll help you a lot. Hope this helped. Oh wait, I got one more slide. Sorry. Last slide here. We talked about this in class on Friday. This is kind of a conceptual problem here for Lenz's law. When you drop two magnets through these two loops, two identical magnets, they're both in free fall. Does the magnet on the left have an acceleration that's greater, less, or equal to the magnet on the right? And the difference is, obviously, you've got a little open loop here. Here you have a closed loop. So try to figure out the answer to that, and if you have any questions about it, you can come in and talk to me.